Good morning. Welcome to IISc Press book release event. The book that is going to be launched today is titled The Computation Meme, Computational Thinking in INDIC Tradition, edited by Professor Kanchi Gopinath and Professor Shailaja D. Sharma. To initiate the program, may I invite Professor Amresh Chakrabarty, Chair, IISc Press, to deliver the welcome address.
Hello, hello. I think it's this one. That's okay. Okay, so good morning and a very warm welcome. I don't know, I wondered whether we should call warm welcome. I think it's a British saying, and their country is rather cold, so probably we should say a very cool welcome to all of you. And again, it's a very pleasant occasion for us to meet every time a book gets published. You know, we were discussing earlier with Professor Gopinath and Dr. Sharma that how difficult it is to publish a book, to start with one's own, and how much more difficult it is to publish a book that's edited, because you have to now get other people to write the book. And you are as strong as the weakest link, as they say. And I'm really glad that this wonderful effort has now finally come to fruition, and many congratulations to the authors and the editors in particular for taking on this onerous task and succeeding in it. So I just wanted to say a few words about IISc Press. IISc Press was started in 2008, centenary, as part of the centenary celebrations, in order to primarily publish books of high quality in science and technology, and hopefully more in medicine very soon. And at affordable price for the Indians. And that's the motto, quality at affordable price. And we try to keep the price of the books around 3 rupees per page, whether it's published by an external publisher or co-published with an external publisher or published entirely by us. So as IISc Press Committee, I'm really privileged to have Professor Justin David, who is sitting at the back. Maybe you can raise your hand. And then Dr. Arpita Patra and Professor Mohit Jolly as our committee members, and of course Professor Kaushal Verma as the ex officio from the Office of Communications. And we publish all sorts of books, monographs, also biographies of great scientists and so on, as well as popular books. We have some of the popular books by Professor Ashok Malik from IIT Kanpur. In mathematics and so on are extremely popular. We also publish books of popularizing science. For example, Arting Science, a book championed by Dr. Vitasta, who is holding the fort for us at IISc Press, has been another very popular book. And we published books not only from India, but also from abroad. So any author who is interested in publishing with us are encouraged to do so. Professor Anurag used to say, who was the first chair of this press committee, that we all have grown in our area by learning from great books. And yet, we do not put enough effort into writing books. And I think that is something that we need to take on. It's much harder and longer, but I think it's worth it because it makes a great impact. And we co-publish, not only publish books on our own, but also co-publish with Cambridge University Press since 2013. As you know, it's the oldest university press in the world. And also with WSPC, the World Scientific Publishing. And we have recently signed contracts both with Springer and one more. Taylor and Francis, exactly. So the idea is that you can decide to publish directly with us, or you can decide to publish, co-publish with one of them. So the book will be jointly published. So with that, I would like to once again congratulate the authors and the editors and pass on the baton to Vitasta. Thank you.
Thank you, Professor Chakrabarty. Now, moving on to the program, may I now invite Professor Y. Narahari, Professor, Computer Science and Automation, to say a few words about the editors and the book.
I would like to wish all of you a very good morning. In particular, my namaskarams to Professor Narayangar, Professor Balakrishnan, Professor Kaushal Verma, Professor Amrish Chakravarti, Professor Vinod Ganapati, and all the distinguished people who have come here. First of all, I really do not know why I was chosen for this role. I have been a beneficiary of IISc Press. My book on game theory and mechanism design was actually published by IISc Press. So maybe that is the reason why I have been called upon to do the duty here. I certainly want to say a few things, both about the editors of this book and also about the book itself. About the editors, especially the first editor, Professor Gopinath, I can say some things very, very confidently. Whereas about the book itself, I am not so sure whether I can say whatever I want to say very confidently. It will be very superficial. First of all, I must say that this is a lovely textbook, lovely edited book, and I have spent about 5 or 6 hours reading various chapters of this book, and I found it very engaging and very, very interesting. First of all, about the authors. I think Professor Gopinath is a faculty member whom I have known for 37 years now, and he has been my distinguished colleague at the Department of Computer Science and Automation. And I still vividly remember, it's still very green in my memory. About 20 years back, I think, I walked into his office, and he gave me a 30-minute, extremely authentic expository description of the Maheshwara Sutras, Ayivun, Rulruk, and so on. And until that time, I always was fascinated by the Maheshwara Sutras, and I did not know the inside out of Maheshwara Sutras. I think that half-an-hour lecture really gave me what it was all about, and it whetted my interest, and I was actually able to dive deeper into Maheshwara Sutras, which come in the Ashtadhyayi of the great poet Panini. And I think for the past several decades, Professor Gopinath has been a champion of the Indic tradition of computational thinking. He would not lose even a single opportunity to talk about it. Whenever there is time to talk about it, he would always talk about it. And then it was very fascinating to hear from him that some of the things that we ascribe to modern technology and so on were actually indeed very well known in the Indian tradition a long time ago. So, for example, the Fibonacci series, he was the one who told me that the Fibonacci series should be called, should not be called Fibonacci series, it should be called Pingala sequence. So these are certain things that I have come to know personally from Professor Gopinath. So naturally, when I opened this edited volume, the first chapter that I wanted to read was about his comprehensive chapter on computational thinking. And I think it's an extremely well-researched, extremely well-written chapter in the book itself. Well, about the second editor, Professor Shailaja Sharma, I do not know too much about her, but I know that she has spent so many conversations. She has had so many conversations with Professor Rodam Narasimha, and she has, and in collaboration with Professor Gopinath, she has been able to put together a wonderful edited volume. And then when I was reading her biography, I think there was one sentence which really caught my attention. She said she has grown up listening to stories and poetry in various languages. I think that's a very significant statement, and I can personally, in some sense, relate myself to whatever she has said. I think in my young age, especially during my 5th year till 14 years. I think I was very deeply influenced both by my mother, Matrushri, Matrushri Nagavenimma, and also my father, Shri Simhadri Shastri. I think what mother told me was stories. She would tell me various different kinds of stories, including stories from all the Upanishads. For example, she would tell me the story of Sikshavalli, Bhruguvalli, and Anandavalli from Taittiriya Upanishad. And she would tell me the wonderful story of Nachiketa from Kathopanishad. I think all these stories that my mother told me have had a deep influence on me. And then in these days of onslaught by all these large language models and modern AI tools and so on, I think if there is a semblance of equilibrium and sort of a balance that I'm still able to retain, I think it is because of some of these very, very nice stories that she had told me during those days. And then the wonderful thing that father did to me was to tell me about an incredibly magnificent book in Telugu called Potana Bhagavatam. So this is the Bhagavata written by Bammara Potana in Telugu. It's an extraordinary work. And during those days, he ensured that I learned at least about 100 verses from Potana Bhagavatam. And to this day, every day, I will be chanting at least 1 or 2 of those verses from Potana Bhagavatam. This is another magnificent thing that happened. So I think I very well relate to what Dr. Shailaja Sharma has gone through in terms of listening to all those stories and also the poetry during her young days, which has deeply influenced her. So regarding the book itself, as I already said, who am I to be talking about a book where there are articles authored by Professor Roddam Narasimha, where there is an article written by Professor R.L. Kashyap, and where there are 2 articles written by Professor Narayana Iyengar, and all the distinguished people have written those articles. I think I am a non-entity here to be speaking about all these articles. However, I would like to say, I think maybe 1 or 2 things only. The first thing is, I think there is a wonderful observation, which is like a running theme throughout the book, the computational meme. I think they have very clearly separated the axiomatic approach from the computational approach. So this is something that I can very well relate to because I have studied a bit of microeconomics, where there is an axiomatic approach and also there is an experimental approach. There is always this deep debate between the theoretical economists and the experimental economists. I think the same theme has been brought out here so beautifully. I think what they have proved beyond doubt is that there is an approach that the scientists of the Indic tradition, starting from all our ancient rishis and so on, they have championed this approach where they will come up with very rigorous computational models. And there is also the data, the empirical observations. And these models are based on empirical observations. Not only that, these models get refined by more and more empirical observations as they go on. So if you look at the modern day data science, AI, ML, so everything is data driven. And you have a mathematical model, and you actually keep refining these mathematical models through more and more empirical observations and data that is being gathered. For example, all the foundational models in large language models are getting refined every day because of all the observations and all the data that keeps streaming in day after day. So I think this has been brought out very beautifully in this book. And this is one takeaway from me from this book. And whatever is happening in AI/ML today or in data science and so on is actually something that the ancient rishis and all the Indic scientists already had practiced and perfected long ago. This is something marvelous. I think secondly, I found that the edited volume itself is extremely rigorous and very scientifically sort of treated. I have not seen, for example, I have seen this book on Vedic mathematics, right? So if I compare the book Vedic mathematics with this book, the difference here is that every single thing is very, very rigorously explained. And this is the way some of the outstanding discovery of those times should be made visible and should be actually announced to the modern communities. So I am hoping that this book will be advertised very well. I was just now talking to Professor Kaushal and Professor Amaresh to find out whether they have a very strong media presence. So if IISc Press does not have a media presence, I think today itself we should have a Twitter account and ensure that some of these wonderful things are very well publicized. So nowadays the younger generation, they don't look at web pages. And I think they have stopped looking at WhatsApp messages also. I think what actually catches their attention is all the media hype. So I hope the IISc Press people here will create a hype about this book so that some of the wonderful things which are embedded in this book are made known to the community worldwide. And we all will benefit and people will understand the rigor and the scientific tradition that was existing, many centuries ago in our great country. So on that note, I would like to thank the IISc Press and all of you for giving this stage to me, to give this opportunity to me to be talking to all of you. And I must thank Professor Gopinath, Professor Shailaja Sharma, and also Professor Narayana Iyengar and all the co-authors of this edited volume for the wonderful contributions. I would like to congratulate all of them, and I would also like to wish glorious success to this wonderful book. Thank you.
Thank you, Professor Narahari. It was wonderful listening to your anecdotes as well. Now I invite the editors of the day, Professor Kanchi Gopinath, and followed by Professor Shailaja D. Sharma to put forward their remarks.
Just nobody's ready. Yeah, can you make it into full screen? All of you, in a cool way, as was suggested earlier, and I thought I will give a certain high-level perspective about the book, and also talk about how this book got started. So I just would like to speak a bit about this. So I think as you see, the book chapters, there are quite a few interesting ones. For example, Professor Narasimha, the article which triggered my interest in this area. Professor M.D. Srinivasa's article, Professor Narayana Iyengar's articles, Professor Datta's articles, and Professor Kashyap, etc. So you can see quite a few let us say, quite a variety of perspectives in this area. Okay? I don't think I'll be able to go through any one of them in any detail, but I thought I'll just show you the chapters. Some of them are about, for example, theory of induction, some of them about methodologies, some of them about astronomy, the Vakya system, for example, some of them about music, some of them are about, let us say, an error correcting algorithm, etc. Okay, so you'll find a variety of articles. All of them have a certain computational perspective, and I think that I hope that you will enjoy looking at it more closely. What I will do today is to give some high-level perspective, which guided my, let us say, approach to this particular way of presenting it. Okay? So let me just start with the article which really triggered my interest. This is Professor Rudam Narasimha's article in EPW in 2003. Article's name is Axiomatism and Computational Positivism, Two Mathematical Cultures in Pursuit of Exact Sciences. And if you look at it, he will say, okay. We'll see the underlined one. He basically says that there are two cultures, and the one which he calls computational positivism, he says is characteristic of the Indian and apparently Babylonians astronomy, and basically how to make computation agree with observation. Okay, this seems to be the high-level perspective that Rodam Narasimha identifies as a key characteristic of Indian thinking. Actually, if you think about it a bit, I thought, let me give you some examples of historically. Let's just take the contrast between the Greek and the Indic perspectives. What you see on the right is something called the Antikythera, which is basically an amazing gadget that was discovered, let us say, on a shipwreck near the Greece somewhere. And basically, it's an amazing gadget. It actually keeps track of multiple calendars plus prediction of eclipses, things of that kind. And it's truly astounding gadget of that time. But if you think carefully about it, it's about one idea of ratioed gears multiplied many number of times. Okay? Or if you think about the Greek idea, it's about Euclid's grammar. It has a deductive style of reasoning, and often it is equated with mathematical thinking. And that's one type of, let us say, you can call a culture of doing certain kind of intellectual inquiry. The other one, I just thought as a contrast, could be, let us say, Panini's grammar, truly mind-blowing grammar. It requires at least a minimum of 1 or 2 years of real hard work to really understand it in any depth. Okay, and it has got amazing ideas. For example, certain rule-based, let us say, models, and oftentimes nowadays closer to be taken as computational. It has got ideas like nested exceptions, how to argue about termination when you're doing rule derivations, and truly amazing ideas. Okay? Or you can take the other approach, something called Chakravala algorithm, and it's a truly intricate algorithm, and it's basically about solving quadratic indeterminate equations. Okay, and this is truly mind-blowing also, in my opinion. Okay, it's truly amazing. Okay, so you can see there's a contrast between the Greek kind of. They're also very good. I'm not knocking one or other. That's not the idea. Greek has a certain interesting perspectives, and the Indian perspectives are slightly on a different plane, but both of them together do something very interesting. That's what I'm going to talk a bit about. Okay? Essentially, if you think about Indian thinking, it emphasizes computational aspects. Kotaka is basically the linear indeterminate equations, okay, linear one. Chakravala is the quadratic one. And I should mention that all this work was done in India, and it took some time. Nothing happened just like that. See, when you import something, it happens just immediately. Whereas this was done homegrown. You can see that Chakravala, it took 6 centuries. Brahmagupta got it going. I'm pretty sure somebody else also must have thought a bit earlier, but what we know from written records is that Brahmagupta got it going, but he solved it to some extent. He didn't completely solve the problem. By the time Bhaskara, about 12 centuries, 6 centuries later, the complete solution is there in all the detail. Okay? And what's interesting also is that Bhaskara's solution is still ahead of what the Europeans discovered in the 17th and 18th century. Okay? Only in the 1930s we really understood exactly in what way Bhaskara's solution is better than the European Gauss and not Gauss, Euler and I'm not sure who else. Okay. Again, if you think about computational model, I already talked about. It is the grammar is a computational model at a level, comprehensive level, which is really amazing. It is. I don't think it has ever been done before or after. Okay. Again, if you look at combinatorics, again, if you look at Kanu is a great computer scientist, and his 4th volume, if you look at his 4th volume, he talks about, because he has a historical perspective also. He reviews all the work done all over the world, and he basically says, for example, says Sarangdeva's, Narayan Pandita's work on combinatorics are both remarkable and well ahead of its time. It's got all kinds of amazing ideas, how to do ranking, something called Colex orders, Qt order, Fibonacci, all kinds of things, amazing things, all that kind. Again, some of you might also heard about infinite series, and this also is Professor M.D. Srinivas is here. He has translated and made accessible some of these amazing ideas in this particular area from Kerala. And what's interesting is that they have a notion of infinitesimals, which actually are very well grounded, okay, compared to the somewhat more, let us say, not so well-founded ideas which came later and finally had to be fixed. Okay? And so there is some very interesting stuff that's going on here. And I think that I'm arguing that there is a certain computational streak running all through our Indian, not only mathematics, but also in other areas. I'm only talking about closer to mathematics right now here. Okay? So if you think about the two perspectives Professor Narasimha talked about, there is one axiomatism, and the extreme version is what is called Platonic thinking. Basically, the idea that Platonic ideas are innate, you just have to recall them, or you pick them up through Socratic dialogues. Okay? In a sense, you can sit in a corner and figure out everything. I'm sorry to caricature it. I'm pretty sure there's something more complex than that. But you can, that one extreme version. And the other version is Feynman. Again, Professor Narasimha also talks about this in his articles. He basically says that there are two ways of doing physics: Greek from first principles and axioms, and the Babylonian. Okay, and he doesn't call it INDIC because I think it was not very clear to them at 1960s when I was writing this that Indian people had any connection with this kind of thinking. And he says that I have no preconception about what nature is like or ought to be. Okay, and essentially not start from a completely axiomatic, or you decide on what are the initial starting points, but you actually look at all the world as you see them and figure out what actually, in some sense, you select something, figure out how they interact, and do something with it. Okay? For example, what Feynman says, relating one thing to another. Okay? Again, you can think this, you can see this kind of idea even in our philosophers. For example, if you look at Sharma, they will tell you that induction is not a valid way to figure out what's happening because the reality is so complex. Okay? Because, for example, what Feynman is saying, he doesn't have any conception of nature. Similarly, the Charvakas are saying that the reality is so complex that all confounders cannot be listed. Okay? There's no way to figure out, when I say something, what something else can actually make that particular statement false. Okay? That confounders are not, all of them cannot be listed. And so Charvakas basically say induction is not a valid pramana. Okay? Similarly, if induction is not valid, it turns out even deduction you have to be careful. Okay? For example, if you say I'm completely deductive, then you can keep asking, where did you get this from? Where did you get this from? You can keep on going backwards. Infinite regress is there. And that's why, for example, in our tradition, for example, Madhvacharya actually says people who talk about deduction as hetuvadins, basically people who, okay, there's a lot of debate in Indian circles about some of these issues. Okay. Similarly, when you talk about deduction, the type of objects involved in this deduction, they also have to be carefully handled. Okay? If you don't handle it well, you get into messy situations. Like I'm talking about this paradox of the heap. For example, you can have two premises. Let's say 1 million grains of sand is a heap of sand. Even if I remove one, it's still a heap. Okay, let's say just the two premises. I can do it any number of times, and finally I end up with 1 grain of thing. Is it a heap? Okay, you can see that even though it looks like a reasonable deduction, okay, of course this is slightly not what a logician will be happy with what this is, but this is the kind of reasoning that we often employ. Okay, when we deal with any real systems, we oftentimes use this kind of approximate kind of directive models. It can all be made more, let us say, more rigorous, etc. But I'm saying this is roughly oftentimes use this kind of thing. So in a sense, what you can say is that even deduction, if it is not carefully done, you can get into mess. Okay? And there are various models of doing things. And notice that anytime you have infinitary arguments, for example, Zeno's paradox, infinitesimals, limits, you get into this kind of mess. And that's why even to this day, there's a lot of controversy about what's called constructive mathematics versus a different kind of mathematics. Okay, the dominant paradigm of mathematics. Okay, look at what is called. I don't want to frighten you with this words, word embeddings and LLMs. It turns out you need to represent a word without a math is to see, Ganita is to compute observations. Okay, so he also uses the word Drugganikaitya, for example. Okay, again, this is Professor N.D. Srinivasa's article, which I picked up this quote, and you'll see that this it may not be widely known, but roughly what I understand of it, I'm pretty sure you'll have some different perspective than me, but I'm just thinking that mathematics is the domain of discovering invariants or symmetries in carefully defined abstract structures through human intuition. Okay? And for example, Hamming says the goal of a process is to give insight. Whereas computation, again, there's a famous computer scientist at Princeton University, Avi Wedgerson, he talks about what he defines computation. Evolution process of some environment via a sequence of simple steps, simple local steps. Basically, the notion of state is very strong in computation. The notion of state is not that strong in the case of mathematics. Okay? So, again, you can see the ideas like two cultures in other areas like statistics. I don't want to spend much time on this. Okay, there are other perspectives that you can also bring back to this particular issue. For example, Cartwright, a philosopher of science, she talks about the fact that, nature is not an easy thing to model, precisely because you don't have closed causal systems. Okay, you might be, even if you are interested in axiomatic systems, the minute there are multiple axiomatic frameworks, how to combine them is a big issue. Okay, and of course, for example, you can do ranking, voting, all those kind of models are there. But again, this is closer to engineering than starting to say that this coming from first principles. Okay. Again, there are issues, even logicians have thought about this. For example, there's a famous logician, Kreisel, for example, from Stanford University. He talks about something called informal rigor, because he's also worrying about if I add axioms or take off axioms, what really is happening. Okay? And even computer scientists have such an interesting perspective on this. For example, Carl Hewitt, 1970s, 1980s, he did that actor formalism, actors. Okay? He basically says that logicism cannot really capture reality because concurrency actually destroys invariants. Okay? So there are some issues of this kind. So you can see from multiple perspectives, it turns out that a strictly axiomatic approach might be problematic. Okay? It might be very instructive, it might be very insightful, but in the real world, there are so many multiple, let's say, frameworks that come to picture. You have to actually somehow get them together. Okay, and that act of putting them together is non-trivial. Okay, and so these various perspectives tell you that there is something deep and interesting that's going on, and probably this computational positivism or Drupganikatya has some possible answer to this particular problem. As I mentioned, there are deeper issues like quantum physics. Those guys, they completely make us have to think more deeply about what is going on. But this is a good starting point, I would believe. Okay. I don't want to. Okay. So I think one of the things that I've noticed is that history of Indian mathematics, unfortunately, I believe, has been written by people who believe that mathematics is completely exclusively deductive in thinking or basically proof-oriented discipline. And I think that because of that, I think the Indian mathematics or Indian computation has got a bad rap. Okay, it is basically thought to be some calculations, simple commercial, calculations in commerce and things of that kind. Okay, so the true nature of Indian contributions in this area has not been properly acknowledged, I think. Okay, and you can see the contrast between some, for example, field medalist like David Munford. He has written extensively about Indian mathematics, and you can see the depth at which he talks about these things. Okay, compared to the regular historians of Indian mathematics. Okay. For example, Donald Knuth also. You look at his book on combinatorics. He really has an amazing chapter, amazing historical section on what exactly happened in combinatorics in India. Of course, Donald Knuth is lucky because he wrote his book. The book came out post 2000, and in 1985 there was a complete translation of Narayan Pandita's combinatorics work, and based on that he was able to get a much better perspective about what Indian combinatorics was all about. Okay, so I think basically, and the book basically argues for a computational running through not only these areas but also in other areas like music and philosophy and astronomy, of course, because astronomy is the place where all this Drupganikatya actually started from. Okay. So I thought recently I was teaching to undergraduate students. I was trying to explain to them what is the difference between computational thinking and mathematical thinking. I thought I will end with one or two simple examples. You'll see that our tradition has explored multiple ways, and this is a simple example. Brahman era, he's talking about what's called combinations. That is, for example, you have k number of things. How many ways you can select r of them? Okay, C of n comma r. I think most of you are familiar with this. Actually, his solution is based on coming up with a computational model. For example, we all know that C of 1, 1 is 1, C of 2, 2 is 1. You can see my mouse. C of 3 is 1, etc. So in a sense, it's some kind of boundary condition. And then you also know that if you look at this one, this side, okay, C of 1, 1 is 1, C of 2, 1 is 2, C of 3, 1 is 3. Okay. And essentially, you'll see that you can construct it by the diagonal two elements that are next to it. You can add it. For example, 6 is 3 plus 3, 35 is 15 plus 20, 120 is 36 plus 84. So if you want to compute this number, 1820, you have to compute these two first, and this has to be computed because these two, this has to be computed because these two, etc. So you can finally come to this. Essentially, it's a computational elaboration. Okay, one by one step you pick up, you basically construct the whole thing. Okay, so it's an example I would call computational perspective. Okay, there's another example which is Mahavira. Okay, this is in the mid-90s, somewhere in Karnataka, actually, somewhere close by. He actually has a complete, what I would call a mathematical formula. Okay, you can see things are there in the tradition, and if you look at last problem, Leelavati, when I first saw it, I solved it using a procedural model. Again, because I'm a computer science guy, so I used a computational model. And finally came with the answer that it is, I don't want to go into detail exactly what this problem is. It's a very interesting problem. But it turns out that it has got a nice mathematical explanation also. Because you can see there are, so when you're teaching undergrad students also, this kind of perspective I believe also helps. Okay. I think I just wanted to, I'm going to conclude in 1 or 2 minutes. Basically, if you look at the article I mentioned, Ruddam Narasimha basically says that if you look at it, seem to continue to do so in the future as well. But, various types of computational positivism are there in signal processing, deep learning, reinforcement learning, game theory, etc. I'm not going to go into it. So I think I'm going to, this is my very last slide. Okay. So in the sense, you can say math and computation are intertwined in a deep way. Math supplies intuition, invariants, or symmetries. If no invariants are available, you just have to do exhaustive check, and that's where the computation comes into the picture. And again, if you think about the Königsberg problem, Euler's König problem, it can be solved very trivially, okay, linear time. But you remove that invariant, it turns out it's some similar related problem, traveling similar. It turns out to be exponential, okay? And essentially, you can say computation uses invariants to anchor itself to extensions, okay? So a lot of amazing, interesting stuff that's happening out here. And I think I don't want to get into, okay. So, okay, I think. I just want to, I'm going to end. I would like to actually thank so many people who have made my thinking a bit more clearer in this area. Professor Narasimha, who really got me started. And of course, this wonderful institution called Indian Institute of Science, and the wonderful institution called Computer Science and Automation, which gave me the luxury of time to think about some of these things, and with great people like Professor Narahari, etc., who, by the sheer example, they made us think deeper about various things. Okay? And of course, IISc Press has helped us quite a bit in making this happen. And of course, Narahari, Ganapati, Chakrabarti, Kushalam, all of you, I want to thank you again for your help here. And of course, the co-authors, and I didn't have an opportunity to meet Professor Kashyap in the process as the book was being done. He passed away, unfortunately. I wish I had, I was hoping to give him the book in person, but we were too late. And so, and I've not met Mr. Bell, who is a student of Kashyap. He's at Purdue University. Nagata is another I have not met. He's a Japanese scholar interested in design, I think, right? And so I also want to thank Professor Shailaja Sharma, because she has gone through my chapter in the book multiple times, okay, with deep critiques about everything. And Kamal Lode also has given it. And I should also mention that this ICPR conference actually was the time when we actually, once we got it going, we actually thought of the book also after that. And again, Ramanujachar and Professor Kannan and Rajaraman. Again, I want to thank my family for putting up with me for when I was working on this. And also the IISc Press, Nilakshi and Chartha, who actually worked with us very closely. And I should also thank Kushal in CSA department, who helped me at multiple. Again, a lot of well-wishers also, I want to thank them. Thank you much. Thank you. Sorry if I took too long.
Namaste to everyone. I put down a few remarks of my own on a sheet of paper because I thought I will make use of this opportunity to share a few thoughts now that the book has come to an end, and we have had some time to think knowledge of these things, and it was just a fortuitous situation that I could be of use and at the same time pursue my interests. So I will just now share some of my own thoughts at the present time on this. For a long time, strenuous efforts were made, and I think rightly so, to establish that Ganita was indeed mathematics, or at least a subset of it, spanning several branches of classical mathematics such as number theory, combinatorics, algebra, geometry, trigonometry, mensuration, calculus, and so on and so forth. However, mathematics itself underwent a significant transformation at the beginning of the 20th century, with David Hilbert repudiating all other approaches to mathematics while taking it to a level of complete formalization, in which even natural numbers were not spared. Although the attempt of Russell and Whitehead to express mathematics as a vast generative library of logical relationships was ultimately unsuccessful due to paradoxes emerging, the reset of mathematics away from intuition and construction to a purely formal system of relationships between abstract entities became the accepted global paradigm, and it has been so for more than a century now. Thus, there is no question that the Ganita of the Indian tradition is mathematics as defined in these terms. The question of whether Indians provided irrefutable proofs or whether they understood what they were doing, what they were talking about, etc., are by now, I think, settled. Some of it in this very volume, and we should or we can move on to other questions. I think it is ironical that the currently dominant paradigm of computation should provide resonance to the ancient Indian tradition of mathematical computation. The very tradition that was until recently dismissed as lacking in rigorous foundations. So it is natural to ask what really changed. This phenomenon of rediscovery of age-old knowledge systems begs the question, was the perspective that led to their early rejection, their earlier rejection, sound in the first place? In the case of media, the quest for reliable knowledge was explicitly not the pursuit of absolute truths, but rather conditional truths appropriate for a given purpose. As an example, one may cite the approximations to numbers such as the ratio of the circumference to the diameter of a circle or the diagonal of the unit square, which, while being recognized as unrepresentable in the rational number system, were nevertheless used with desired levels of precision as per the requirements of the problem under consideration. Meanwhile, the theory of numbers continued to develop with new problems and solutions, showing that science can progress with conditional knowledge. In his essay, Is There an Indian Way of Thinking?, A.K. Ramanujan, cited by the late Professor Rodam Narasimha in one of his lectures, presents the view that Indian thinking permits contextual statements and rarely permits absolute statements. I would like to take this a step further and advance the view that the most significant difference between the Indian and the ancient Greek, which is also called the Western way of thinking, is the presumption of universal beliefs and epistemic certainty. While the Western quest has been for universal and inviolable beliefs and a way to justify and enforce them, the Indians and perhaps also other civilizations have not advanced the need for such beliefs. Belief, which is also called faith, is a central tenet of Western thinking and is assigned a high position in describing human nature alongside of reason. Reason and belief, somewhat paradoxically, go together and form the ground on which the edifice of science is constructed. Even when the beliefs are tentative and described as hypotheses, the endeavor is to sustain or update the hypotheses. In the Indian way of thinking, at least about the world of the senses, I dare say that there is no premise of such beliefs, or for that matter, any type of intellectual absolutism. In a wider context also, there is a diversity of views and no requirement for uniformization. Wariness towards theories, especially on explanations based on inferred necessity, due to the unavoidable hidden presence of confounders, informs this skepticism. The scientific pursuit is by and large not to establish this or that hypothesis or to refute, but to better describe phenomena. This approach does not presuppose beliefs, although it has a place for plausible narratives and models, along with room for revision. For example, that the earth is spherical is inferred by Aryabhatta from his observation of eclipses and of distant terrestrial objects. But he does not feel the need, nor do his successors, to prove it mathematically once and for all, or to make a dogma out of it, or a premise for all future models. The study of astronomy proceeds without, say, Aryabhatta's laws. He notes it as a detail that may be relevant to his computational models. By avoiding the path of irrefutable proof and necessary truths, and preferring the use of plausible, exchangeable models, the Indians took, in my opinion, the most scientific position possible, that of a computationally grounded empiricism, supported on occasion by inference and described by updatable computational models. This amounts to a systematic method of doing science. Further, it acknowledges the persistence of change in phenomena. It is famously said that mathematics is unreasonably effective in solving practical problems despite not trying to do so. But would the subjugation of natural phenomena to the irrefutability of mathematical theorems distort or limit our understanding of physical phenomena? Theoretically, removing the requirements of mathematical models should widen the solution space for problems. And so it does. In such a case, what is our guide to the truth or to reliable knowledge? Alignment with observation again remains the key thing. The only thing, ultimately, which guides us to reliable knowledge. This is as true of clinical trials as of astronomy or behavioral economics, etc. In any case, Indian computational empiricism distinguishes itself from other empiricist approaches in the history of world civilizations by its unbreakable link with computation. I would go so far as to say that the Indians hitched the body of science to the machinery of computation. And the emphasis here is on the word machinery. This machinery was later replaced by the Europeans with mathematics, and the whole thing was yoked to mercantilism, and then the course of history changed, but that's a different story. The computational empiricist view requires acceptance of the reality as it is, rather than as somebody wishes, expects, or claims it to be. Finding a vocabulary and a grammar that can describe observed phenomena is what the Indian method guides us to do. This seems to be at the foundation of the approach towards all disciplines treated of in the texts that we refer to as classical Indian sciences or knowledge systems, which are too numerous and very diverse, cannot be enumerated, or not to be enumerated right now here. Number is as fundamental to this approach as is language, and computation enjoyed the same attention and nurturing as did grammar. A final word as I conclude. It is interesting to note that the term Drigganitaikya does not posit a third pillar, namely yukti or reasoning. It is not essential in this view that inference align with the observed and the computed. The misalignment of yukti would not break the back of the computational model, as the search for different logical paths would, I presume, continue. Thus, perhaps different logical arguments may be presented, but in the final reckoning, it is the alignment of the data and the computational model that is the goal. Thank you.
Thank you to the editors. Now we come to the most important part of the event today, the formal release of the book. For this, may I invite Professor Vinod Ganapathy, Chair, Computer Science and Automation, to formally release the book. May I also invite Professor Narhari to the dais, the two editors, Professor Amrish Chakravarti and Professor Kaushal Verma to the dais.
Open this, I can hand out a copy. Please, Shailaja, please come. Professor Gopinath was kind enough to give me a copy. Right. Yeah, come.
From this side.
Congratulations. Which was second book, Professor Gopinath? Second book.
Congratulations to the editors and to all the authors. May I request Professor Vinod Ganapathy to say a few words, please.
So, good morning to everybody. First of all, many congratulations to all the authors and to the editors, Professor Gopinath and Professor Shailaja, for this really wonderful book. Professor Gopinath was kind enough to give me a copy of the book last week. And although I must claim that, this topic is entirely new to me, I had a chance to read Professor Gopinath's chapter. I was fascinated by one thing, right, which is the number of footnotes in the book. And the number of deep references that were given to, algorithms that we are taught in school. For example, the greatest common divisor, square root. All of these things were connected back to history, and I found that really fascinating. My own connection is, Professor Gopinath. I met him first in 2005 when I visited IISc for the very first time as a PhD student, and he was my host at that time for a talk that I gave. And I had been interacting with him in the field of computer systems, computer security, and so on. And only when I joined the institute in 2017 did I realize that he was a scholar in these aspects as well. And we used to have occasional conversations about the INDIC tradition. And he had a project as well that was recently, I think, in 2017 funded along these lines. And it's really a pleasure to be able to inaugurate this book. Thank you very much, and congratulations to the authors and the editors once again.
Thank you, Professor Ganapathy. We are fortunate to have three of the very distinguished authors of the book amongst us. May I request them to also say a few words? May I first invite Professor M.D. Srinivas to say a few words.
Namaskara. It's indeed an honor to participate in this book release function. I have come mainly to convey my thanks to Professor Gopinath and Professor Shailaja Sharma. It has taken a very long time since the idea germinated in terms of the conference, and I'm sure the articles also evolved quite a bit. And I'm glad that IISc has acknowledged the area and the importance of this work and has come out with a publication, which I'm sure will both enhance the scientific community around to the need for discussing these kind of issues. Professor Narasimha's initial material, which was put together by Dr. Sharma, based upon his lecture in NIAS, I think, a couple of years ago, before his passing away. I knew Professor Rodam Narasimha for quite some time, but in this context, I saw him some very philosophical sort of appurtenances which go into formulation of a planetary model. They differed. If one reads the preface of Ptolemy's Almagest, the purpose for doing astronomy and how it is to be done, and what are its premises, and what is to be taken for granted. And if one reads anything, Bhaskara, Aryabhatta, Nilakantha, the way the astronomical text goes about talking about everything. And Ptolemy talked about the fact that astronomy is so important because the celestial motions were indeed so regulated that a true philosopher should indeed, or a true mathematician should indeed go in for this. Whereas, as Aristotle said, the motion of bodies in the what is called the sublunar sphere, they were so random and really there was nothing for philosopher to do. And again, for the ultimate origin of all this celestial movement, the prime mover, he was again beyond the scope of our understanding. So it is astronomy which is giving eternal, unchanged laws about planetary motion. And that is what is worthy of a true philosopher to pursue. The preambles to Indian books would say that this is a Kala Nirnaya Shastra, Kala Vidhana Shastra, and a major chapter of astronomy text would say how to find out the longitude, latitude of a place, direction, and time. And this, of course, it said about various other things. They started with an invocation to either to the planets or to the creator or everything. It's not that they were bereft of a larger framework in which astronomy was to be embedded, but the astronomy was astronomy. It was about trying to find out time, a mundane thing like trying to compute or understand time in the terrestrial level and our position, latitude, longitude, and directions. A large amount, even Nilakanta's Tantra Sangraha, the largest chapter is what is called the Chaya Adhikara of 400 odd verses, 150 verses around the better and better ways of doing this. And this was to be done by observing the motion of the celestial bodies and being able to compute it, etc. And therefore, astronomy indulges in this. So Professor Narasimha was very happy with this chapter, and he then showed me the paper, with the precursor to the EPW paper, which he wrote. He had written a paper, I think, for an international conference on these different approaches of science. That was there very evidently between the Greek and the Indian, and to some extent between the modern and the Indian. And this was really true historically. We talk so much about Panini today, and we talk so much about the interaction between India and the Greek civilization. There is literally nothing said in any Greek account about Sanskrit language. All Greek accounts, nothing about Panini at all. And all that they said was India was a land of large number of languages. It was, Herodotus said this had the largest population. Whereas the Chinese, who really came to study Sanskrit, and they studied Sanskrit in, this I Ching, who comes in 7th century, he's studying Sanskrit in Sumatra for 6 months. And then he comes here and says that Panini Sutras are very highly regarded from Vietnam to Uzbekistan, all over the world. Of course, they are very highly regarded truly in India, the land of celestial wisdom, the storehouse of celestial wisdom, and the divine land of China. So, it was, while civilizations interacted, these kinds of different perspectives, they did not pass through easily. And that would have happened, when Western Indologists write about Indian astronomy, They wonder how, when they are supposed to have borrowed, according to them, so much from the Greek models, even the simplest thing that Ptolemy did is not taken, or even the understanding of the exact, the Euclidean proof of the volume of a sphere is not taken in India. And this would go back there also. So these different ways of doing science, ultimately Professor Narasimha is right. In modern terms we can put it between Feynman and Dirac, as he has written. I think it doesn't come out in this article, but he has separately written about it. But there is something funny there too. Feynman called himself a Babylonian, and Dirac, of course, was worried about the symmetry and beauty of the laws of physics and the niceties of the equation. But when our own great mathematician Harishchandra, he went from Baba to Dirac to pursue his PhD, he became much dispirited because he found Dirac too much bothered about the empirical validity of his equations rather than on the theoretical structure of the algebra of Dirac matrices and what can be done about their representation theory and all that. And so within a couple of years he moved away. He found Dirac too much involved in empirical matters rather than the theoretical structure of the mathematics that is coming. And he moved on to a very profound branch of mathematics to which he contributed enormously. So what I'm trying to say is that there is a continuum between this theoretical sophistication and the worrying about the empirical validity. The way to do things, whether our theories give them actual handle to do them. And there many historians think that the Chinese do not worry about theories at all. This was some remark of a 8th, 9th century Islamic scholar. He said the Greeks worry only about theory, and the Chinese do not worry about theories at all, and it's the Indians who have a theory and they worry about how to go about doing things. But I think the focus on what we today call as algorithms, which are called as parikarma, vidhi, prakriya, karana in all our older texts. This is not just in mathematics, not in astronomy. It is so in Dharma Shastra also. It is so in darshanas also. So all of them describe ways to going about doing something. But they have a theoretical framework which sort of supports the particular way that they are advocating. And there is a lot of debate about it. And there is a lot of question as to when do you empirically sort of verify and say that this prakriya is correct or that prakriya is correct. So this has been the whole corpus of Indian knowledge is filled with all this debate. And I think we cannot easily take a position that we were bereft of theory or we were concerned all. The older idea was that Indians were idealists. They only looked at their navel or at the sky. And the later idea is that they were too much of empiricists. They are worried about this Rigganitaikya rather than about the Ganita. So I think this entire corpus has to be very carefully studied. But it is indeed true that when we did the various Siddhantas, the evaluation of the Siddhantas was how good they were in actually producing good algorithms for doing things. So the goal of science was not to reach an ultimate Siddhanta. I mean, science as it concerns the observable world, human world or material world, how we live in it. And for that, it's not the ultimate theory that matters, but have all these various methodologies at our hand, which are simple, which are useful, beautiful also. So that kind, and bring out ways of going about, even in the context of modern knowledge, that will be extremely significant and vitally useful for re-establishing our own civilizational ways of understanding knowledge. I thank Professor Gopinath for giving me this opportunity. I thank all of you.
Thank you, Professor Srinivas. Now I invite Professor R.N. Iyengar to say a few words.
Namaste to all of you. Thank you. For me, it is a homecoming. I spent the best part of my life at this institute, nearly 45 years, when I joined 1963 as a student and retired in 2005 formally. So I'm a little bit emotional to come here. When Kanchi Gopinath asked me whether I would be coming to the release function, I said yes, because IISc, even though I stay in the other part of Bangalore, want to come and see the institute. Even though I may not go to my parent building, which is the next one, at least here I wanted to come. Now I want to say a few words about my involvement in this subject. Srinivas has already spoken about so many philosophical issues, and Kanchi Gopinath has said about several modern things on science, whereas the work that I was involved was very mundane, down to earth. That is working about earthquakes, actually. So one of the questions which used to come up was about history of earthquakes in India. Why we don't have any data about earthquakes before about 200, 300 years. And I was involved in some of the safety issues with the nuclear reactors. And when in the international forum, when we talk about safety of nuclear reactors, it was being mentioned that you have to consider a 10,000-year earthquake, at least the type of forces which come on that, so that even though the structure may be economically valuable for about 100, 200 years, it has to be safe for nearly 5,000 years or so, because of various other considerations. Now, that puts a question. There have been earthquakes in India, obviously, and are there earthquakes in Gujarat, which are mentioned previously? Many people would say, even the common man, yes, Krishna's Dwarka went down because of an earthquake or because of a tsunami and all that. The question comes up, when was that? Is it already 1 lakh years old, or only about 3,000 or 5,000 years old? And should that not be factored into the safety of our infrastructures in this country? It's a very important question. So when I looked into Mahabharata for finding out what may be the cause, what are the kinds of earthquakes, yeah, there are earthquakes mentioned in that, but you can't date them. Now, the usual thinking is Mahabharata is about 3000 BC or so. But when I went through the data which is available in the text, because we don't have any archaeological information yet which is verifiable, which belonged. When I was in engineering, civil engineering, we were taught about theodolites and a little bit of astronomy. I tried to put the things together and see what was the most probable time these observations were done. That didn't match with 3000 BC at all. That is another story. But I was exposed to a different kind of thing, which was all what I did here at Indian Institute of Science only. That the astronomers astronomy for which we are so famous, starting from Aryabhata and onwards, they had no idea of what was the astronomy which was before that period. I may be wrong if you take it in the overall sense, but I will be right if you see the details. For one thing, no mention of comets at all in the Aryabhatan astronomy or in the Siddhantic astronomy. Why? They calculated the eclipses and all that. There are no mention of comets. Mahabharata has comets. And when I looked into the literature which is prior to Aryabhata, there was mention of comets. And that is what interested me, because as a naturalist interested in natural science, not specific to some particular area, were Indians not interested at all in natural sciences? That was the question. That was wrong, actually. They were more interested in natural sciences than in mathematics, than in astronomy. They were interested in so many things. And that came out in a publication called Parashara Tantram, which I edited, and it was released by, in fact, Professor Rodam Narasimha in 2013. And there have been comets, and the comets can give us also an idea of what was the kind of history this country has gone through, what kind of disasters that have happened in this country. So it is the disasters which interested me to look into the more ancient period, and I found that that was the best intellectual period in this country if I go only by the data that is available. There has been tremendous development in the Common Era, in particularly the first millennium of the Common Era, starting from, I would say, Aryabhatta, or even a little bit before that, even if you include Pujit Dwaja and others, there has been tremendous development. But there was a higher peak even before that. That was before Kautilya, including Kautilya's Arthashastra. If you see before that, the Vridagarga, Parashara, these people, what they did, Vridagarga's text is available as a manuscript, which I am editing. I have added some of that into this. They were all observational people. So the observational astronomy is slowly becoming computational. That's what Dr. Kanchi mentioned, Darshanam Ganitan Jaiva Yugapad Yoga Sadhakam. He says, should not go only by Ganita, should not go only by observation, because they wanted to know what was the position of moon in the morning, with which nakshatra moon is associated in the morning. Today, you know, there's so much of horoscopy, so much of talk about these things, and you know what is your birth nakshatra and all that. How do you fix up when a person is born in the morning? What was his birth nakshatra? That is the question that Vridagarga raises, and then interpolation comes into picture. When you know something about moon, his movement observing in the night, along with the nakshatras, because they did not have any other coordinate system, so this is a slow development of that, and that intellectual development is what attracted me. And that was the exact place where music also comes into picture. Because that was the period when, from the chanting of the Vedas, the classical music was getting separated out, like in the Bharata's Natya Shastra, which is generally dated to about 200 BC to 200 AD or 100 AD. Bharata mentions about vibration of strings, how two strings have to be vibrated and how they resonate and all that. Well, I spent, as I said, all my life working about vibrations, starting with vibration of strings, finding out the natural frequencies of buildings, bridges, and a variety of other things. So it interested me, and we all love the classical music of this country, which I have also been liking. Then suddenly it turns out, when you read the books which are there in Sanskrit on music, they all look at the nature. When they want to explain a raga, he says, it is like the wind blowing, the rain falling and all that. Yeah, that suddenly interested me. I was working also at the Center for Atmospheric Sciences, where apart from earthquakes, we would work on rainfall. And it was a computational positivism, as Narasimha would call it, data analysis. Large data analysis, multidimensional analysis, finding out fitting in Gaussian and non-Gaussian models for this natural phenomenon, trying to see whether I can predict rainfall for the next year. We did quite a bit of work on that. But the comparison in the Sanskrit text about ragas and the natural phenomenon attracted me. And then I thought, well, there are invariants in classical music. Somebody was mentioning about invariants in mathematics. The ragas are invariants. Whoever sings a particular raga, you recognize it. Maybe a child, or maybe a maestro, or maybe it is an instrument. There is something invariant which is generally called arohana, avrohana, or whatever. It is an attractor. So the raga has to be within a bound that is an attractor for it. And there are different ragas, different attractors also like that. And hence, I thought I should investigate this because of the little bit of probability theory I had studied, again at the Indian Institute of Science, whether that can fit into the classical models of music. It does. Only difference is they did not have the symbolism, the modern symbolism, but they had a little bit of meta-language, which of course Panini had already developed, like you can have different sutras. Even the language of Sanskrit is described in terms of a meta-language, which is we can call it higher Sanskrit, because even T, to, do, they can all be derived as a shabdas and things like that. The question of what we say in the modern, even in the newspaper, sargam, sari, gama, and all that, that is actually a meta language for a particular frequency, and it is the relative ratio which is taken as music, not the absolute, the sounds themselves. So these are some of the things which attracted, and try to put all these things together, starting from Bharata's Natya Shastra, and see how the theory of probability originated in India, not by De Moivre and all those people, but they have worked on it, of course, no doubt. I studied probability theory only from those books, but I could see the comparison between these. And classical music as a random process is what interested me, and what interests me even to this day, and how there is a sensitivity to initial condition, that the same person sings the same raga but differently each time when you listen, and you have that enjoyment. And all this is, the basic fundamentals comes from Samaveda, that is from the Vedic period, whereas in the Rig Veda there are only 3 pitches, only 3 swaras, whereas in the Yajurveda slightly later on. There is a development, as somebody was telling, this did not happen in one day. It has happened over thousands of years actually. Whereas when it comes to Samagana, there are 5 swaras. Some people say there has to be 7 swaras also. And later on we have the classical music development. Well, I don't want to take too much of your time. I just wanted to mention that science, there is something which we may very confidently call Indian science or Indic science, which has originated in this country from the most ancient people. What shall I say, chest beating, glorification, wine glorification, but that is not necessary. That is hard science, scientific thinking, and that is sufficient to keep this country in the forefront as a civilizational example for scientific thinking, rational thinking. Well, these few words, I thank Dr. Gopinath and also Dr. Shailaja for giving me an opportunity to contribute something to this wonderful book. I look forward to see the book also. Thank you so much.
Thank you, Professor Iyengar. Now I invite Professor A.K. Datta to say a few words.
And not to speak. And also in my mind now something is hovering on in my mind, that is division by zero. Because I'll be talking on division by zero just this afternoon at 2 o'clock in the Department of Mathematics. And if some of you are still around, you could just drop. At Department of Mathematics, at 2 o'clock I'll be talking about division by zero in Indian mathematics, which has been almost invariably criticized in accounts on history of mathematics, and I would show that why it is justified. What the Indians did was justified. Anyway, so first of all, hearty thanks to Professor Gopinath and Professor Sharma for the opportunity to contribute to the volume. Particularly, I was going through a difficult time, and I was not able to attend the conference from which this originated. But Professor Sharma particularly had been in regular in touch with me, and because of her, my contribution kept on increasing. So initially I wrote some 3 sections, then she kept on asking various questions. So if you find that my article is too long, the blame is to Professor Shailaja Sharma and not to me.
That's about all articles.
Yeah, okay. Now more seriously, just as a supplement to what Professor M.D. Srinivas had been saying about that this Indian tradition, it cannot be really said to be this or that. And this theoretical or, there was this feeling that it is always, it had been theoretical and not actually doing, experiments or observations. And then the pendulum went in the other direction, that there was no theoretical basis, etc. One has to be careful about characterizing the mathematics in India, because I'll give you one example that this characterization has often been used to deny certain things which have taken place. So, for instance, the Pale's equation that was highlighted, what is now called Brahmagupta-Pale's equation, in various slides it came about that x square minus 61 y square equal to 1. So more generally, dx square plus 1 equal to y square, solving it in integers. Now this problem was started by Brahmagupta and solved within a few centuries probably by Jayadev. Now, a very eminent mathematician, and I should say that he has contributed much to the development of modern abstract algebra, and a very meticulous historian of astronomy and mathematics, van der Waerden, he argued that this work was of Greek origin, and the primary thing was that Brahmagupta, why he was interested in this. So he gave this thing, that Brahmagupta was an astronomer. Why should he be interested in this equation? So I have no other explanation, I meaning van der Waerden, than there must have been some work done by the Greeks before, from which Brahmagupta copied. He also used the word copied. It's not that I'm saying it sarcastically. He used the word copied. And this is not, coming from politicians or journalists. It is coming from van der Waerden. Now, the thing is that this excessive assertion that we don't do the Greek kind of mathematics. We are interested in what is, what would be useful for common man. It has its impact. So, for example, let's say this Hogben's book, Mathematics for the Millions, they have said, the author has glorified, I would say, the Indian contribution to zero, the decimal system and algebra. But then he says that why is it that in India invented the decimal system and this algebra and not the Greeks? He said that because they were not, they didn't have the Greek kind of sophistication, so they were, practical people, and because they were practical, these things came up. So this is so you see that this kind of sinks in. So when you see something of a high degree of abstraction, you immediately, somebody like van der Waerden immediately says that this could not be of Indian origin. This completely ignores. Now the thing is that Brahmagupta was, like the Gauss of his time. That this is big man. So Gauss, was he a mathematician or a physicist? Now you can say that Gauss was a physicist. So this work in number theory could not have been his. Now everybody will laugh at that if one makes such a statement. But that is a kind of statement which is made about Brahmagupta. So here one has to be careful about this characterization that Greek kind of thinking was not there in India, and that is not, something useful in any case. This kind of statement goes against. And Brahmagupta's work like this, what now goes by what is called this modern abstract algebra, whose fundamental principle is composing. That is something which occurs in Brahmagupta in the context of solving Pale's equation. But since we have been always emphasizing the algorithmic part, now the composition law itself is an abstract law. It's not an algorithm as such. So always it has been, how to say, that even in Indian accounts of mathematics, it had never been given its due. when I have been invited to give talks on Indian works in indeterminate equations, I've always been requested to talk on the Kutaka and Chakravala algorithm. And I changed the title. So I was asked to talk on Kutaka and Chakravala. I made the title Kutaka, Bhavna and Chakravala. Bhavna is Brahmagupta's composition law. That stands out on its own. So it has been always, even in Datta and Singh calls Brahmagupta's result as a lemma. So here, this is the first time in world that a composition principle is introduced in mathematics. This you don't find anywhere, and I mean that kind of thinking would come only much later in Euler and more strongly in 19th century in Galois, etc. So this principle of composition he is introducing in a matter-of-fact way. This has got just missed in even in account of the Indians. I mean the Indians who have been trying to highlight in a positive way. So I would like to. So what I would like to emphasize is that not to have biases about various features of mathematics and then associating like and so that things which don't fit into the patterns that we have set, we tend to ignore. That I have a certain model about what is Indian mathematics, so if this doesn't fit, then I don't highlight it so much. So so like Brahmagupta's result, it has been, I mean the algorithm, the Chakravala algorithm is the main thing, and Brahmagupta's thing is a useful lemma for that. Because of putting it that way, it never got highlighted. And once this has been highlighted, particularly in the previous decade, you can see the difference in attitude of mathematicians. So for example, there is an excellent mathematics magazine, and it has been named Bhavna as a reference to Brahmagupta's law, which is called Bhavna. So something which was kind of not in the limelight as the great achievements in Indian mathematics. So that has been used to name this. And I'll name one Fields medalist, Manjul Bhargav. He worked on, he became famous because of his higher composition laws. So Brahmagupta's laws were generalized by Gauss. I mean, not Gauss didn't know about Brahmagupta, but he gave a general composition law. And Manjul Bhargav simplified Gauss's work and gave new compositions law, which surprised everybody because no one expected that anything can be done after Gauss. Now, what I'm trying to say is, what I would like to draw your attention is that if you look at Manjul Bhargav's initial papers in Annals of Mathematics, he doesn't mention Brahmagupta. So when somebody does something, he mentions the previous contributions there. So he mentions Gauss. He does not mention Brahmagupta till 2006. In the 2006 ICM talk, he mentioned Brahmagupta for the first time. And now, invariably he mentions Brahmagupta. So for instance, when he was giving a talk on Ramanujan, he was asked about mathematicians other than Ramanujan, in whose work he found that magical element which characterizes Ramanujan. So he mentioned three of his modern mathematicians. And then he says, if I go further, I'll mention Gauss. And if I go still further, I'll mention Brahmagupta. The work that he did in 600 AD just blows your mind. So in a talk on Ramanujan, he mentions 5 mathematicians who had such a magical quality. And in the reverse chronological order, he ends with Brahmagupta. So this is the thing is that when this work is seen as the first example of composition, the attitude of mathematicians who are at the forefront just completely changes. And this is a far cry from van der Waarden's thing that the entire work, not forget about composition, the entire work could not have been Indians because Indians were interested only in astronomy and practical things. They were not interested in this kind of things. So one has to see things in the proper perspectives. Yes, I got lost track of that. When I was mentioning about Gauss, you see, Brahmagupta's has 24 chapters in Brahmashputa Siddhanta, of which probably only 4 are on mathematics, and only 2 are available in English, as far as I know. There's one on Ganita, which includes arithmetic and geometry, and one on algebra. So 2 out of 24 is a very small amount. So you tend to think of astronomy him as a primarily as an astronomer, and mathematics is subservient to it. But the 2 chapters are rich, absolutely rich in mathematical content. That gets that gets lost in the volume of astronomy in which those 2 chapters are embedded. So these are certain things we have to be, and lead to things which I had exemplified. So thank you.
I would like to begin by thanking the principal editors of this volume, Professor Gopinath and Professor Shailaja, and the contributing authors who have put in a lot of work to produce this wonderful volume. The process of curating a book is like going from ink to print in some sense. The whole thing starts with an idea which the authors have to convert into a good manuscript, and this has happened in this case, undoubtedly. But once the manuscript is ready, then begins a completely different process which is invisible to the external world largely. And I would like to take this opportunity to place on record my sincere thanks and my deep appreciation to the entire team who has been part of this. I'd like to begin with the IISc Press Committee that my friend and colleague, Professor Amresh, has been managing for many, many years now. We also have on board wonderful colleagues like Professor Justin, Professor Mohit Jolly, and Professor Arpita, who've been helping with all the coordination work that goes into such an initiative. The Office of Communications staff has been instrumental in taking care of all the backbreaking work that goes into producing each single page that you see in the book. I would not like to miss the designers and our printers. These are people whom you do not see on occasions like this, but if it's not for their efforts, their meticulous planning and cooperation and patience, we would not be seeing this book today. Professor Narhari mentioned publicizing the book. That is a point that is very well taken. I must add here that apart from the usual channels of social media which seem to rule the world today, the Office of Communications has also started curating podcasts of all authors of IISc Press books, as well as guest editors of each issue of the Journal of IISc. So Professor Gopinath and Professor Shailaja, we will be reaching out to you one more time. We would be very thankful if you could spare a little bit of time for this effort. These podcasts have been going on for at least 2 years now. We put them up on various channels. This is just our way to thank the authors and to also publicize the book and to let everyone know about it. Having said that, I would also like to thank everybody here in the audience. No event is complete without the participation of people on the other side. Thank you for coming. Whenever a book is released, IISc Press organizes such a function. It is our way of thanking the authors. It is our way of publicizing the event in person. And it is our way to tell the world that we appreciate scholarship and depth of work. Thank you very much for being here, and have a good day. Thank you.
Thank you, Professor Verma. We would also like to mention that there is tea outside. Please join us for tea. And the book is being sold. You can get the editor's signed if you buy the book today. Thank you.